Okay, so we'll continue on here, and in the textbook, it takes a break, kind of in all of this t-test stuff, to just point out that the difference between association and causation. And I know this is something we've covered earlier in this class, but it's worth pointing out again, just because all too often people will jump to the wrong conclusion. Okay, and so in a t-test, we are looking at group 1 versus group 2. And we compare the means, right? And so at the end of your study, you might come to the conclusion that the means for population 1 and population 2 are indeed different, okay? So at the end of the t-test, we might reject the null hypothesis and conclude that mu1 is indeed different from mu2. Okay, and we might be tempted to say that group 1 is doing this thing and group 2 is doing this other thing, and that's the reason why they are different, okay? But we should not say that, okay? Differences between mu1 and mu2 are because group 1 is blank and group 2 is something else. Okay. And all we can say is that a difference between mu1 and mu2 is associated with the two groups, okay? The only way we can make these causal conclusions is if group 1 and group 2 are established through random assignment in a controlled experiment, okay? So if group 1 and group 2 are not created via random assignment in an experiment, we cannot conclude that the differences between group 1 and group 2 are responsible for the difference between mu1 and mu2. And so this is that's one of the limitations of statistical analysis, is that we cannot jump to these types of conclusions. Okay, and this is all detailed a little bit more more formally in section 7.4. Okay, so moving on, we'll go more into t-tests, and specifically we will look at one-sided or directional t-tests. Okay, so one-sided tests are tests where the alternative hypothesis has either greater than or less than. Okay. Versus, you know, if the alternative has not equal, then it's a two-sided or non-directional test. Okay, and pretty much the entire process is the same, except in the process there's an additional step that you do at the beginning. Okay, so the process for a t-test is largely the same, except at the beginning you must perform a directionality check. Okay, and at the end, I should say, and at the end, you do not double the tail area.
Are you saying that if the alternative hypothesis has a not equal sign, then it's not a t-test?
No, I'm sorry. Then it is a two-sided t-test or a non-directional t-test, I should say. Two-sided t-test or a non-directional.
So the next sentence is the process for a one-sided t-test.
Oh yeah, I'm sorry. The process for a, yeah, that is, I left that out. Thank you.
Sorry.
No, that's important. I don't want to have bad notes here. Yeah, the process for a one-sided t-test is largely the same as a two-sided test, except at the beginning you must perform a directionality check, and at the end you do not double the tail area. So let's get into this. Okay, so what we are saying is that let's say we want to know if a drug reduces blood pressure, right? Okay. Does a drug help reduce high blood pressure? This is what we wanted. Okay. So you take some patients, okay, and let's say they all start off with high blood pressure. Okay, so you get so here's our experimental setup. So this is not the best setup, but let's say this is what we do. Okay, so experimental setup, you get a bunch of patients with high blood pressure. So I think that's defined as like over 140 or something. Over 140 systolic. All right, so and then we do random assignment. Random assignment. Okay, so we get group 1 gets the placebo, and group 2 gets the experimental drug. And we measure their, let's say we get 25 in group 1, and in group 2 we also have 25 patients. Y bar 1, Y bar 2. I'll fill in these numbers in a moment here, okay? In S2. So the null hypothesis would be what? Mu1 minus Mu2 equals 0. This means no difference. So this is, I'm sorry, this is their blood pressure after, I don't know, several weeks taking either placebo or drug. Okay, so we record systolic blood pressure after several weeks on the drug or placebo. Okay, so null hypothesis would be that there is no difference between the ending blood pressures of placebo and experimental groups. Okay, between the blood pressure, recorded blood pressure of placebo and experimental groups. Okay. And but what we are curious, the alternative, we are not interested in just, is this difference non-zero? Okay. We are actually only interested if we have evidence that the experimental drug is effective in reducing blood pressure, in reducing high blood pressure, right? Okay, so if it turns out, if our evidence ends up showing that the experimental blood pressure actually didn't even lower blood pressure, but it increased it, this is a failure. This is, we're not going to even bother pursuing the statistical analysis. You know, if the resulting blood pressure of the experimental drug is higher than that of the placebo, we know right off the bat this thing doesn't work. Okay, so we're only interested if the experimental drug shows a reduction. Okay, so in that case, mu1 minus mu2 should be what? Greater than or less than 0? Group 2 is our experimental drug. Yeah, greater than 0. Okay, so in this case, what we're basically saying is that the blood pressure of the placebo group is higher than the blood pressure of the experimental group. This would be the only alternative that would be of interest to us, okay? If we get the result where the blood pressure of the placebo group is lower than the blood pressure of the experimental group, this does not support our cause for trying to market this drug, okay? I think the history of Viagra is that they were trying to find a blood pressure medicine, but it wasn't actually effective in reducing blood pressure, but the side effect that was reported was of interest to the company. So anyway, so okay, so let's say, all right, so I'm going to just start off with one set of numbers, okay, to illustrate this process of performing a directionality check, okay? So let's say the placebo group, their mean average was 142, and the experimental group was 147, okay? And then our standard deviation, it doesn't even matter, okay? When we look at this, we have to do a directionality check, and that is, does the data we have match the directionality of our alternative hypothesis? Okay. And in this case, the experimental drug, the people who took it actually end up having higher blood pressure than those with the placebo. Okay, and so in this case, there's no sense in continuing the test. We are not going to have any evidence of supporting the alternative. Okay, so actually, I'm going to copy all of this onto the next slide. Okay, so if y bar 1 is equal to 142 and y bar 2 is equal to 147, we will certainly not have any evidence to support the alternative, okay? If anything, it appears that our experimental drug increases blood pressure, which is exactly what we don't want. Okay, so this is the directionality check. You look at your data and you check to see if the data is aligned with our alternative. And in this case, it's not. Okay. So I'm going to say this fails our directionality check. And if it fails your directionality check, you can say we will not reject the null hypothesis. And we have no evidence to support alternative. Okay, but let's say this wasn't the case. So I'm going to just cross these out, and let's say this was 147, and this one ends up being 135, and I don't know what this is. 25, and this is 30. Who knows? Okay. So now we check the directionality. Okay, so this time y bar 1 is 147 and y bar 2 is 135. Okay, so in this case, our values for y bar 1 and y bar 2 match the directionality of our alternative. So we will continue with our test. Continue with the test. Okay, so maybe I will give you a few minutes to come up with the test statistic and resulting p-value. Okay, so test statistic is y bar 1 minus y bar 2 over standard error. Standard error is the root of s1 squared over n1 plus s2 squared over n2. Okay, so I'll pause the video here and I'll give you guys a moment to figure this out. Let's take a look here. So for my standard error, I'm getting root 61, 7.81. So my test statistic ends up being 147 minus 135 divided by 7.81. So 12 divided by 7.81. And I get 1.536. Alright, so I'm going to look this up in the t-table with degrees of freedom equal to 25 plus 30 minus 2 with 53 degrees of freedom. I go to the table and I don't see 53 degrees of freedom. Oh, I'm sorry, 25 plus 25. Oh, I am doing this entirely wrong. Okay, so 25 plus 25 minus 2, 48 degrees of freedom. Again, I go to my table and I'm going to look at 40 degrees of freedom. Okay, so we use, because we always round down. So I'm going to look up 1.536, 40 degrees of freedom. So 40 degrees of freedom, I get 1.536 goes here. And that is in between 0.10 and 0.05. Okay, so our resulting p-value this time, because it's one-sided, I don't double it. And so my resulting p-value is my tail area, which is going to be between 10% and 5%. Okay, so from the table. Is that good with everybody? Okay, and so let's say, let's use, because alpha is not specified, so we will use alpha equal to 0.05. So we assume alpha is 0.05. So what do I conclude? What is my decision? Yeah, my p-value is greater than alpha. So our conclusion is, do we reject or do not reject? We do not reject, and we do not reject which hypotheses? Yeah, we do not reject the null hypothesis. Okay, and what does that mean with respect to the blood pressure medication? Yeah, okay. So there is a distinction here, and I have to nitpick. Okay, so this means all we can say is we do not have evidence that it reduces blood pressure. Okay, so this is what we must say. We do not have evidence that the drug reduces blood pressure. Okay, that is not the same thing as the drug doesn't work. Okay, it doesn't prove that the drug is completely ineffective. It does not prove that. all it says is that, you know, we looked at 25 people for the placebo, 25 people with the drug, and, you know, we got this difference of 12 whatever points. And that is not enough evidence to say that the blood pressure that the drug reduces blood pressure. So we have to say we do not have evidence that the drug reduces blood pressure, but do not say that the drug is completely ineffective, or that the drug doesn't work or has an effect of 0. Okay, I know it feels, you know, we didn't reject the null, so we feel like we can just say stuff like that, but there is technically a difference, and so if we want to stay true to, you know, what we are allowed and not allowed to say, what we are allowed to say is we don't have evidence that the drug reduces blood pressure. Okay, and you know, that's statistics. We have to say all of these boring, unexciting things. But so this is what we have. Okay. Is all of that okay? All right. So I want to relate this back to confidence intervals. Okay. So confidence intervals, we did something very similar. We looked at 2 samples and we compared their means, and we created a confidence interval for mu1 minus mu2 based on 2 samples. And your conclusion there was also, if the confidence interval contains 0, we said what? We do not have evidence that mu1 and mu2 are different. Okay, so this should be reviewer familiar. And on the other hand, if the confidence interval did not contain 0, okay, we do have evidence that mu1 and mu2 are different. Okay, and compare that with our hypotheses tests. And especially a 2-sided hypothesis test, a 2-sided t-test, meaning the alternative. All right, I'll just write alternative is that mu1 doesn't equal mu2. Okay. Essentially, these are equivalent. Okay. A t-test, 2-sided. Maybe I'll plug that in there. A 2-sided t-test with alpha equal to 0.05 is equivalent to a confidence interval, to a 95% confidence interval for mu1 minus mu2. Okay, and with alpha equal to 0.10, this is equivalent to a 90% confidence interval. Or in other words, with significance level is equivalent to basically 1 minus alpha confidence level. So if you use the same data if data creates a 95% confidence interval, that goes from let's say 2.1 to 14.7, whatever that is, okay? Then we have evidence that mu1 and mu2 are different, right? Okay. If we use the same data, for a two-sided hypothesis test, okay, then we will reach the same conclusion. I should say two-sided hypothesis test with alpha equal to 5%. I need to specify that.
So the conclusions will be the same, but the numbers will be different. It's different calculations.
Right. You're doing different calculations. So then we will reach the same conclusion. Okay. So, it doesn't tell us anything about what the test statistic is, but we do know that our p-value will be what?
Less than
5%. Okay, so we will reach the same conclusion. So we know that the p-value is less than alpha, or is less than 5%. Okay, and vice versa. The flip side is also true. So if we conduct a two-sided hypothesis test with alpha 5% and we reject the null hypothesis, then that means the corresponding 95% confidence interval will not contain 0. Okay, so let's try a few thinking problems here. Yes.
So when we say we have evidence, doesn't necessarily mean that we don't assume that it's true. Right?
We don't assume what is true.
Like we have evidence that they're different. It still doesn't mean like they are definitively different, right?
No, so in the case, so when we say we have evidence that they are different, we are rejecting the null. And I guess nothing is definitive. We don't know for sure what the population looks like, but we say we have evidence that they're different. And essentially we come to the conclusion that they are different, For example, when a jury convicts the defendant, okay, we conclude the defendant is guilty. Now, if we were omniscient and knew exactly what happened, we may actually know that through an elaborate setup, the defendant was actually innocent, but there was all this overwhelming evidence pointing towards the guilt, we might figure that out. But for, you know, all intents and purposes, when the jury says guilty, the person becomes guilty, you know.
So, do you not have evidence?
Yeah, but the flip side, if the jury does not convict, that doesn't mean the defendant is innocent. Okay? Because we always assume the null hypothesis. So we assume the null hypothesis, or we assume, you know, innocence, and so when there's enough evidence to reject that, then this becomes kind of the reality or the truth. But if we don't reject it, it doesn't actually prove that this is true. We just assume that it is.
Like false negatives and false positives.
Yeah. So if we don't, if we don't convict the defendant, if the defendant is found not guilty, we just continue to assume that he or she is innocent. But it doesn't prove their innocence, okay? And proving innocence is a much more challenging thing to do in an investigation. And, you know, very rarely will an investigator say, we have concluded so-and-so are innocent. And usually that's like in a case of trying to exonerate someone who's been falsely accused. Okay. I just saw this movie Gone Girl. I don't know if you've seen that.
I read the book.
It's really
Okay.
good.
Yeah, okay. Well, I can't speak anything of this, but in case you intend to watch it, I don't want to give any spoilers here. It messes with your head. All right, so let's try a few things here. Okay, so you perform a two-sided hypothesis test. I'm going to just abbreviate it HT, with alpha equal to 5%, okay? You do not reject the null hypothesis. So this is the establishment. I've provided you with no data, okay, other than this information. So now I'm going to ask you a few questions. If you had used alpha equal to 0.01 instead, what would your conclusion be? And we will say if you had used alpha equal to 0.10 instead of 0.05, what would your conclusion be? If you use the same data. To make a 95% confidence interval, would the confidence interval contain 0? And We'll do the same question, but this time okay, so think about this, and do your best in answering these. And I'll pause the video here. Okay, let's take a look. So from this, it says you perform a two-sided hypothesis test with alpha equal to 0.05, and we do not reject the null hypothesis. So what do we know about our p-value? We know our p-value is greater than 0.05. Okay, so we can use this to answer at least our first question here. Okay, so if you had used alpha equal to 0.01 instead, so using the exact same thing, we would get the same p-value, right? Using the same data, we would get the same test statistic, we would get the same p-value. And we don't know exactly what that is. All we know is that it's greater than 0.05. So if we have alpha equal to 0.01, we know that our p-value will also be greater than 0.01. Okay, and so that means, what would your conclusion be? Do not reject the null hypothesis. Okay. On the other hand, if we had used alpha equal to 0.10 rather than 0.05, in this case, we know our p-value is bigger than 0.05, but we have no idea if it's bigger or smaller than 0.10. Okay, our p-value could be 7%, it could be 25%. We don't know. Okay, so here we do not know. Okay, p-value could be bigger than 0.1, it might not be. Okay. If we use the same data to make a 95% confidence interval, would the confidence interval contain 0? Okay, so over here, the 95% confidence interval, the conclusion we make here needs to match the conclusion we make here. Okay, and so the conclusion up here was that we didn't reject 0, we don't have evidence of a difference, right? So we do not have evidence of a difference at alpha equal to 0.05. So we will make the same conclusion with a confident 95% confidence interval. And so if we're not going to have evidence of a difference, then that means our confidence interval does contain 0. Okay. Okay, and so with a 90% confidence interval, that would be equivalent to using alpha equal to 0.10. Okay, so we do not know the conclusion, the decision at alpha equals to 0.10. So we do not know if the 90% CI will contain 0. There's also the notion of statistical significance versus practical importance. Okay. a lot of times, let's okay. So statistical significance, this is rejecting the null or not rejecting the null based on the p-value, okay? All this says is that our result is not a result of random error alone or random chance alone, okay? That's all it says. It doesn't tell us if what we observe is practically important or not, okay? You need to be knowledgeable in the field that it pertains to in order to make that conclusion. Statistics in of itself can only tell us whether or not it could have happened by random chance alone, okay? So this only tells us if our results could have happened by random chance. Actually, rejecting the null, this only tells us our results could not have happened by random chance. I should keep it all together. So rejecting the null based on the p-value, this only tells us our results could not have happened by random chance alone. Okay?
The practical importance is if you're in the field.
Yeah, the practical importance generally depends on whether you're in the field or not, something like that. So for example, and this is a book example that shows up in our, what is a p-value anyway? Perhaps you want to know if taking the shortcut home saves you time, okay? So you can think of different paths to get home, and so you take a stopwatch and you record the average time it takes to get home on path 1 and the average time it takes to get home on path 2, okay? And after a bunch of data collection, you do a statistical analysis, and maybe it comes to the conclusion that indeed the shortcut saves time. Okay, statistically significant amount of time. On average, it saves you 42 seconds. Okay, you take the shortcut, you will save 42 seconds on average. Okay, and it is statistically significant. This result could not be a result of random chance alone. Is that an important difference? Does it make a huge difference that you are saving 42 seconds? Maybe, maybe not, okay? Probably for most of our regular people, 42 seconds is not going to make a huge difference. And on top of that, let's say the shortcut home involves driving through a sketchy part of neighborhood where you don't feel comfortable or something, okay? And so now you have to weigh, is it worth saving 42 seconds? And if it means I'm going to have to drive through this part of town that seems a little bit shadier or whatever it might be, these are the questions that only you, the driver, can answer. Statistics can just tell you this 42-second difference you observe is not a result of random chance, but the fact that the shortcut is indeed faster, okay? But is that important? Maybe, maybe not, okay? I think it would be unwise to just say this is statistically significant, we see a difference, therefore this is the best choice to make, okay? Everybody wants to save time and everybody wants to spend less time driving, but I don't know. Does it matter? Would you tell your grandmother to take the shortcut, to save her time? Maybe, maybe not. Maybe that's not the best choice. Okay. So, let's see. Okay. And on the other hand, okay. So, yeah, I don't feel like writing anything there. Maybe on the side of practical importance, we can also just somebody can say, I'm interested in implementing this new thing, but only if it saves me at least $1,000 a year or something like that. Okay, and so you kind of whoever the expert in the field says, or the decision maker says, they're willing to implement change if it's going to save $1,000 a year or something. Maybe you do a study, and based on your statistical analysis, you come to the conclusion that there will be a statistically significant difference, but that significant difference is only $600 a year or something. So in that case, you have an example where it is statistically significant, but because of the definition that the boss has made, it is not practically important, or it's not large enough to cause us to implement the change. Or maybe you create a confidence interval around that value $600. You create a confidence interval, and maybe it goes from, I don't know, 500 to 700. In that case, it's still not practically important. Okay. On the other hand, your confidence interval could go from, let's say, 900 to 1,050. Okay. And so now you have this question: is it did we cross the threshold or not? And that one we cannot answer based on the information we have. Okay, we can say it could be over 1,000, it might be under 1,000. Okay, and I don't know. In that case, you should probably talk it over with the boss and say, it might save us over $1,000. Maybe it only saves us $970, but if it saves us $970, maybe it's still worth implementing or something like that. There's some question there. So anyway, all this to say, it is unwise to just say 5% yes, no, and unwise to say statistically significant, therefore good or bad. Okay, all of this you have to take into context of what you're doing and make decisions accordingly. Okay, so yeah, I don't feel like writing all of that out, but that will be my my lecture of trying to impart wisdom regarding the application of these statistical tools. Okay. This week I'm skipping the last section in Chapter 7. The last, there's a little bit more that you have to do a little bit reading. You can skip the section on planning for power. You can read it if you want, but I'm going to skip that. And we're also skipping section 710. Okay, we'll cover that next week. I will, however, cover one or two sections from Chapter 8. And this is on the paired t-test. Okay. Chapter 8, Section 1. This is the paired t-test. All right, and so in some situations we have paired data. So all of the stuff earlier assumed that our samples were sampled independently, so that one sample had nothing to do with the other sample. The two groups were independent. In this case, our two samples share a link, okay? And so we call them paired data. A common scenario is before versus after. Okay. We want to know, is there a difference before and after? Okay, and so we take, two measurements on the same subject. So this is when we would apply the paired t-test. Okay, and so here's a silly scenario. Let's say some company markets the magic weight loss pill. Okay. All right, and so let's take a look. Okay, and let's say we have before weight and we have the after. Okay, and so let's say somebody starts off at 225. After taking the pill, they are down to 220. Someone else starts off at 190, and after the pill, they are down to 185. Another person starts off at 260. After the pill, 255. And someone else starts off at 160 and ends up after the pill 156. Okay, so Y bar and S. Let's I'm going to use vanilla R just for this. So we're going to get mean of 225, 190, 260, and 160. So 208.75. And let's get the standard deviation there. 43.277. Okay, let's do the next column. 220, 185, 255, 156. Oops. So that's a mean of 204. And standard deviation 42.9. Oh, okay. Okay. I can actually we can do a t-test on in R. And I just do t.test before, comma, after. Okay. And so if I do the before versus after, I don't know if you can see this, but it says my test statistic is 0.1559, and our p-value is 0.8812. Okay. So if we did the work ourselves, we would get something very comparable to this. When we look in the table, it would just see p-values greater than 20% or 10% or something like that. And actually, yeah, it would actually be half of this because this is doubling the tail. So the incorrect method, incorrect approach, is to treat the samples as independent. Okay, so the incorrect approach would use null hypothesis mu1 equal to mu2, and the alternative mu1 is greater than mu2. Okay, it's one-sided because we want to know if afterwards if they lost weight, right? Okay, because if we do this, our test statistic t would end up something like 0.155, 0.156, and we would get a p-value greater than, 10% or something like that, or 20. What's in our table? 20%. P-value greater than 20%. That's not what we want. Okay? What we need to do, and if we look at the numbers, it actually seems like you take the pill, you lose about 5 pounds. Okay, we don't know what's happening, but at least with this data, with the 4 people who took the pill, they all lost about 4 or 5 pounds. Okay, so it seems like the pill actually works. And so what we need to take into account is the individual starting weights. And so I'm going to create a new column called the difference column, because with the incorrect approach, what's happening is that the weight loss, the difference of about 4 to 5 pounds, that gets kind of muted out in comparison to the standard deviation, the variation between individual starting weights. Okay? However, if we look at the difference, if we do before minus after, we see this guy lost 5 pounds, this person lost 5 pounds, this person lost 5 pounds, this person lost 4 pounds. Okay? And so we're getting a very consistent weight loss of around 4 to 5 pounds. Okay? And so in this case, I can calculate the mean of these weight change numbers, and I'm getting a mean of 4.75 and a standard deviation of 0.5. Okay, so the appropriate approach, correct approach, is treat them as paired data. Okay. All right, and so there's an important distinction here. Is you calculate the difference column, and then this is the only column that matters now. You ignore the other 2 columns. Okay, so once you calculate the difference column, that's the only one that matters. And then the hypotheses you use are also different. So we are no longer looking at mu1 and mu2. We are looking at the mu of the difference. And the null hypothesis is that the mean difference is 0. And then the alternative is that the mean difference either is greater than 0, less than 0, or not equal to 0. So in our circumstance, we want that mu difference to be greater than 0. Okay. So do not, for the hypotheses, it is incorrect to say mu1 equal to mu2, because that implies independent samples, two populations. Here we have one population, and we're just looking at the difference that the weight loss pill induces. Okay. Our data is then, we have 4 data points, and to indicate the mean difference, we use d bar is 475, and standard deviation of the difference is 0.5. Our test statistic would then be, again, observed minus expected divided by the standard error, or in our case, what we observe is d bar minus what you expect in the null hypothesis, 0, divided by the standard error, which would be S over the square root of n. So we have 4.75 minus 0 divided by 0.5 divided by the square root of 4. Okay, so this is very much, or it's pretty much the standard error for the sampling distribution if you have one sample, or the confidence interval when you just have one sample, right? S over the square root of n. Okay, and so in this case we see our test statistic ends up being a very large 19 standard errors away from the mean. Okay. So we will get our p-value, seeing that it is one-sided, will definitely be less than 0.0005.
How do you calculate the degrees of freedom?
Oh, degrees of freedom is n minus
N minus.
n minus 1. Degrees of freedom is n minus 1. Okay, we have one sample, so it's just n minus 1 degrees of freedom.
Is that n divided by difference, or is that n divided with degrees of freedom up there? N equals 4t equals 4.
So it's s over the square root of n.
No,
or-
it says data.
Oh, I'm sorry. Yeah, n, and this is d bar. It's a separate symbol entirely. Not n over d. It's n, and this symbol is d bar, like y bar, but d for the difference. And the textbook uses a capital D, so I apologize for the discrepancy there. Okay, and so, you know, I could do the same thing here, t-test before and after, and I'd say paired equals true. And I don't know if you can see this, but it says our test statistic is 19. I have 3 degrees of freedom, and my p-value ends up being 0.0003. Okay? And to indicate that it is significant, statistically significant, and we would conclude, you know, reject the null, and we have evidence. There is positive weight loss with the pill. With the magic pill. Such a pill does not exist, though. But and it might, you know, if there was such a thing where you take a pill and you lose 5 pounds, it would probably be abused and
all
sorts of stuff.
Different pills that say they can make you lose weight, are those are not done with people with statisticians?
You know, so there are actual weight loss pills that have been past the clinical trials and are approved by the FDA, and they operate on different mechanisms. But there's nothing that you just take it and you lose 5 pounds instantly. I think one inhibits absorption of oils, and so it has its own set of side effects and stuff. But there are things that. Huh?
You think this test would have been better for the blood pressure experiment?
Yeah, well, so we haven't talked about experimental design. So paired tests probably are better suited for, you know, is the effect of this thing true or not. So pair tests are good. The rest of Chapter 8 is all about paired samples. We're actually going to skip over the rest of that. You can look at it, but you don't have to. I'll mention it a little bit more next week when I just wrap up Chapter 7. Okay, so we'll end here, and we'll see you guys next week. There's a quiz covering t-tests, paired t-tests, and stuff like that. So, okay.